Howdy hi, AP Calculus BC, and welcome back to our polar section of Topic 4, Parametric Vector and Polar. This is the first of our 2 days where we're going to do a deep dive on specific polar graphs, and we're going to try to do accomplish or learn a few things here. First, we want to be able to create these polar graphs with a decent degree of accuracy, and second, we need to understand why the graphs look the way they do. And then third, as a bonus, we'll incorporate some calculus from last class too with our derivatives. So our first day is on exploring rose-petal polar graphs. This first page is going to use the equation r equals 4 sine of 2 theta. Now, if you want to look back to your notes, or if you might remember, what would you expect this graph to look like, and what's it called? Well, hopefully this doesn't come as too much of a shock based on the title, but this is going to be a rose petal graph, right? So, and again, I had made the comment before, it doesn't really look like a rose to me. We grew roses growing up, and I think this is kind of different. However, that's the name it's called, so that's what we're sticking with. And there are two things you need to know about rose petal graphs. First, you're going to need to know the longest length of a petal. And second, you're going to need to know the number of visible petals. You might be thinking, wait, visible petals? Why would there be invisible petals? And we'll discuss that at length as we go through. So we're actually not going to fill those in yet. We'll do that in just a second. The first thing we're going to do is create this graph using a table. I think a table gives a good understanding of how polar graphs are created, and we're going to need that when we start finding area. And B, it's going to show us which values I'm going to substitute in to find some nice radius values back out. Let's begin. We have theta and r. Theta is our input, r is our output. I'm going to keep track of these over on the left side over here. Don't forget, though, that polar coordinates are written strange. They're written as an output, comma, an input. So you can kind of make your own little table as we go down here. It doesn't have to be perfect. And I think it's just going to be easier to keep track of the points on the left so they don't get mixed up with the table on the right. So let's begin. 0, and we need r. What is r? Well, we should probably remind ourselves that r was 4 cosine, I think it was sine, wasn't it? It was 4 sine of 2 theta. There we go. 4 sine of 2 theta. Easy enough. And whenever we evaluate points, we just plug the 0 in for theta and find r. The first couple I'm going to show the math for, and then I'm going to pause and have you guys fill in the rest. Okay, so it looks something like this. We're going to do 4 sine of 2 times 0, which of course will simplify to 4 times sine of 0. Sine of 0 is 1, 4 times 1 is 4. Great. What point did we just find? We just found the point. Oh, no, sine of 0 is 0. Awkward. We just found the point 0, comma 0. Yay! Second point, pi over 12, 4 times, the sine of 2 times pi over 12. We have to do a little more simplification here, but hopefully it's nothing bad. You might be thinking, sine of pi over 12? You never taught us how to do that one, and that's true. We don't know how to do that one. But don't forget that the 2 and 12 reduce and leaves us with pi over 6, doesn't it? And sine of pi over 6 is a pretty nice value. That's 1/2. So we have half of 4, which is 2. Next one, 2 comma pi over 12. And we'll try one more just to make sure you got the hang of it, and then have you fill out the rest of these. So last one that we're doing together, 4 times the sine of 2 times pi over 4. These again will reduce to make pi over 2, and this time I think I'll get the sine value correct. Sine of pi over 2 is 1. I'm much more confident of that. 1 times 4 is 4, and we found the point radius of 4, rotation of pi over 4. Now that we get the idea, let's get some trig practice in, please, and try the rest of just the first table. We're not going to do the second table yet. Don't cross it off because we're coming back to it. But just fill out the rest of the first table and stop when you finish with pi, please. Ready, set, go. Alrighty. Hopefully you saw a bit of a pattern here too. We'll go 0, 2, 4. This one's going to give you 2, and then we're back to 0. So 2 comma 5 pi over 12. Then actually I'm going to take over in a new color here, and we're going to say that this is 0. And the reason I'm taking over in a new color is because we've already been to 0 once, and I want to see the difference here. So 0 comma pi over 2. And then guess what? You'll find as you plug in these values, you kind of repeat the same pattern. But when you do this one, and we should probably take a peek at it, I actually screwed this up earlier, so I'm re-recording this section, much to my chagrin. We have 2 times 7 pi over 12, which becomes 4 times the sine of 7 pi over 6. 7 pi over 6 is all the way down here. It's in that third quadrant, and we need to remember that anytime you have sine in the third quadrant or fourth quadrant, that sine's the y-axis. The y-axis is negative down there, so we're going to get a negative result, right? Negative half of 4 becomes negative 2. So this one is negative 2, comma, 7 pi over 12. Okay? And now the rest of the pattern just repeats itself from up above. I don't know why I did that in red when I said I was switching colors, but that's all right. We can just write right over this and still be okay. But here are the rest. You'll find that this is negative 4, negative 2, and 0. Now, if you forgot the negatives, easy enough to put back in there. I'm going to fill in the rest of these, and then we'll get to the graphing portion of things. And then, once again, because we've already been to 0, I'm going to switch colors a third time, and we'll go to green. Nice. Now, when we plot these points, we're going to take this list over here and start plotting things. We're going to need to know where they all belong on this polar graph. And this polar graph came completely unlabeled, which I actually like. It's intentional because it helps remind you of where your rotations are, especially on a unit circle. Okay. Now, we can start with maybe the easiest of them, which are pi over 4s. I think pi over 4s just subdivide each quadrant, or I guess each half of our grid into 2 pieces, right? 1 pi over 4, 2, 3, 4 pi over 4. So let's fill those in. 1 pi over 4, 2 pi over 4, but that reduces to pi over 2, 3 pi over 4, and then 4 pi over 4 is just pi. We could also call this one 0, and then we continue through to the rest of these, right? 5 pi over 4, 6 pi over 4 is 3 pi over 2, 7 pi over 4, and then 8 pi over 4, which is the same as 2 pi. I'll put a comma there so we know that they're both accurate. All right, what comes next? Pi over 3s are actually pretty tricky, but I'll show those first because otherwise pi over 6s get weird. So pi over 3, we somehow need to divide this upper section into thirds, and the way we do that is use these upper ones that are right here. Those look like pretty even thirds, don't they? So we start at 0 pi over 3. Here's 1 pi over 3, 2 pi over 3, and then 3 pi over 3 is the same as pi. So we do the same thing down below, 4 pi over 3, and 5 pi over 3, finishing with 6 pi over 3, which is 2 pi. Pi over 6s, let's begin. Might be a little harder to figure out how to subdivide into 6 parts, so why not take one quadrant and split into 3 even parts? 1, 2, 3. And we know that this is pi over 6, but then you might say, well, that's not pi over 6. You're right, it's 2 pi over 6, which of course reduces to pi over 3. 3 pi over 6 is here. 4 pi over 6 also reduces. 5 pi over 6 can't reduce that, so that one ends up there, and so on and so forth. 6 pi over 6 can't reduce, or can reduce. 7 pi over 6 can't reduce. 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. Excellent, and then we're back to the beginning. Nifty. Let's get these graphed. 0, 0. Well, that means go a turn of 0 radians, so we're actually right on the positive x-axis, and then it says go out a length of 0. It's still the origin. Go us. Now this next one might throw you for a loop, pun somewhat intended, because we're doing 2 pi over 12. And you're like, wait, we didn't show any pi over 12s. And you're right, but we did show a 2 pi over 12, because if you multiply pi over 6 to get common denominators, this becomes 2 pi over 12. And so if that's 2 pi over 12 and this is 0 pi over 12, I think pi over 12 must be somewhere right in the middle. And I'm not going to draw in those lines. I think it gets more confusing as you do it. But either way, you can hopefully picture that we're drawing a radius out here, but then we're only going out a length of 2. So right about here, give or take. and the rest are pretty easy. 4 comma pi over 4, also pi over 4, 1, 2, 3, 4. And then 5 pi over 12, well this guy is 6 pi over 12 right here, so 5 pi over 12 must be right before it, and we're only going out a radius of 2. And then we end back up at the origin again. So do we just have 4 disconnected points? Of course not. I only picked 4 or 5 rotations of theta here. There's an infinite number that are happening. And so if this is 0 and this is pi over 12, think about things before pi over 12, like pi over 13, pi over 14, pi over 100, right? So what ends up happening is we draw a radius out before I get, so if this is my rotation right here, there's all this space before. And so if I only rotate a little bit, then we're going to be out just a bit here, and then it's going to be here, and then it gets really close to this guy, and then, well, why don't we just connect all those points, because we hopefully know at this point it's going to curl a bit, and the reason we know is because we should know what the graph looks like. And then it'd be the same thing over here. We draw out a radius and put a point at the end, draw out another radius, put a point at the end, another radius, point at the end, but of course it's probably much quicker just to connect all of these around and back to the origin. So what's happening? I always like to throw a couple arrows just to show the direction that this graph was created. That'll come back and be important later on. But we have made one petal of our rose. I'm so proud of us. All right, but we've only graphed half of our points, so let's look at this next set that I'll do in blue. And you're like, oh, next set, that's exciting. We're probably in the second quadrant right now, and you're like, okay, 7 pi over 12. Well, we already talked about 6 pi over 12 is here, so 7 pi over 12 is right here, yeah. So we're going to rotate to this pi over 12 line, 7 pi over 12, but then our radius is negative, and we know how to deal with that. So we've rotated over here, but instead of going out in a positive direction because our radius is negative, we find that same line and track it the other way, and this will actually bring us down to the fourth quadrant. So negative 2 comma 7 pi over 12 will track us negative 2 down towards, in air quotes, 7 pi over 12. And there's our first point. Okay, what comes next? 3 pi over 4 comma negative 4. Well, here's 3 pi over 4, but negative 4 will bring us out towards 7 pi over 4 and give us this point. And then we have our next pi over 12, which is 11 pi over 12 out here, but then we have to move a negative direction of 2 towards our other. This will be 23 pi over 12. And then we are finally back to the origin at 0. Okay, so we just rotated from here to here, and when we did that, we created the points over here, eventually ending back at the origin. And so what does that look like? Well, we first created this point, and then this one, and then this one, and now we're back here, showing some arrows of the directions we went, and we're doing well. Okay, now our table only gave us the part of the graph in quadrants 1 and 4, but we also only evaluated this at theta values from 0 to pi. So how do we find our last 2 leaves that we would expect? Well, we use the rest of the values from, this time, from pi to 2 pi. But how do we know what to plug in? Because neat old Mr. Grant didn't actually give us theta rotations here. We'll just follow the same pattern as before. I clearly used pi over 12s, right? Because pi over 12s are getting multiplied by 2 every time, which reduces to being over 6. And so I think our first one here is going to be 13 pi over 6, right? And then if we follow the pattern over here, the next one's a pi over 4 value, an odd pi over 4. So I think that'll, let's see, 13 pi, that should be over 12, awkward, is right here. But then the next nice value is going to be 5 pi over 4. So good there. And then why don't you pause and see if you can fill in the rest of the theta values, just continuing our journey, right? We stopped here. Now we said 13 pi over 12, 5 pi over 4. It's going to be this pi over 12 is next, and so on and so forth. Fill those in, find your values of r, we'll see how you did, and you should be golden. Ready, set, go. Alright, and you're back. Hopefully everything went okay. If you're looking at your values of pi over 12, it went 1, then 5, and then 7, then 11. So the first one and the third one were 4 apart, and these were also 4 apart. So if this is going to be 13 pi over 12, the next one's going to be 17 pi over 12. And then we get to our quadrantal angles, lands on the quadrant, and so this one's going to be 3 pi over 2. And then we begin the pattern again. All right, how far apart are 1 and 7? They're 6 apart. 7 and 13 are 6 apart. So if we go 6 more, that's going to give us 19 pi over 12. 7 pi over 4. And then we said that these ones are 4 apart, so we continue 4 more. 23 pi over 12. And we finish at 2 pi. Look at that. Hopefully you've already filled in your R values, but we'll do one of them just to see what the heck is going on here. This one is going to be 4 times the sine of 2 times 13 pi over 12. This becomes pi over 6. Okay, so we have 4 times the sine of 13 pi over 6. That one's a little trickier. Okay, we know it's going to be some form of 1/2, but what form of 1/2? Well, let's see. 1, 2, 3, 4, 5, 6 pi over 6. 7, 8, 9, 10, 11, 12 pi over 6, 13 pi over 6 actually right here is coterminal with pi over 6. So really we could just find pi over 6 and we'll have the same thing. Pi over 6 is positive 1/2. 4 times positive 1/2 is 2. So this one is going to give us, let's erase those extra pieces, all the positive values just like we found over here. 2, 4, 2, and then last color, 0. Guess what? Our last set will give us negative values. Negative 2, negative 4, negative 2, and finishing off with 0. Let's get these graphed. You'll notice that because, and I did these in green, because these are positive, we can just plot them. Oh, I should have done that one in blue. I'm all over the place, sorry. So here's blue. Here's the second one that we did. There we go. Good enough. Okay, third set is going to be this guy in green, and because we're positive, this is 13 pi over 12, and we go out a radius of 2. You can see that this leaf will be in the third quadrant. So 2, 4, 2, 0, and it is drawn in this direction. Excellent. And then last but not least, we are at 3 pi over 2 comma 0, and then 19 pi over 12 is right here. But you'll notice all of our radii are negative, which is going to take me into that second quadrant where we'd expect to be 2, 4, 2, and then finishing off with 0. And here's our direction, like so. Alrighty. Now you might say, wow, that was really tedious. Do I need to draw like this and make a giant table every time we have a problem? No. Again, the point of this is not to have you do this every time. It's to A, see how the graph is created, and then B, help us answer some questions about the graph. In fact, this will be, I think, the only table you make for the entirety of today. We will do one more table tomorrow, though. So what do we need to know about this? Well, jumping back up to the top, we needed to know the length of a petal. Well, we really mean the longest length of the petal. So how far is it from origin to the end of the petal? This is going to be 4 in all directions. We can just see that by counting out. So the length of the petal is 4, and we learned last class that that came from the number out front. And then the number of visible petals, well, I count 1, 2, 3, 4 visible petals, and we learned that last class we just double the coefficient that's attached to theta. Awesome. What's next? How many times does the graph touch the origin on the interval 0 to 2 pi? Using algebra, find the exact theta values where this occurs. How many times does the graph touch the origin on the interval? Well, I think the origin is right here. And isn't that where r is 0? Whenever r is 0, no matter where you rotate, if r is 0, it's going to bounce you right back to the origin. So why don't we just take our polar equation and set r to 0? Okay, so we have r equals, and then it was 4 sine of 2 theta, and we're going to set r to 0. 4 sine of 2 theta, we should probably divide by 4 sine of 2 theta. Uh-oh. These ones are always tricky, our multiple angles. I always prefer, and I'm going to kind of do a little side substitution over here. I like a little u substitution, and so we're going to go ahead and let u temporarily simplify the interior to be 2 pi. So we find 0 equals sine of u. We should be able to solve this. Sine of what is 0? Well, let's start listing some solutions. We get first sine of 0 is 0, sine of pi is 0, 2 pi, and so on and so forth. So we could probably say that u is going to be 0 plus pi k, right? Multiples of pi to move us on up. That looks pretty good there. But of course, we weren't trying to solve sine of u, we were trying to solve sine of 2 theta. So now we're going to take this u, replace it with 2 theta, then I'll show the rest in red. And we're actually going to use this guy down here, 0 plus pi k, and finish solving for theta. Divide everything by 2. 0 divided by 2 is 0. Pi divided by 2 is pi over 2 with the k tagging along. Awesome, except we want to know how many times the graph touches the origin. It is an infinite number of times, but they said from 0 to 2 pi. So let's list them out. And we do that by picking values of k, usually starting at k equals 0. When k equals 0, this cancels and we get 0 plus 0, which is 0. When k equals 1, we get 0 plus pi over 2, which is pi over 2. When k is 2 pi over 2, those cancel, and we get 0 plus pi, which is pi, and hopefully from here we can see the pattern. We're just adding pi over 2 every time, which is what we set up above. So this is going to be 3 pi over 2, and then 2 pi. Great. We found that theta, when theta is those 5 values, our graph will come back and touch the origin. So how does that help us graphing-wise? Well, what this is really doing graphing-wise is it's showing us all the places where theta is, or where r is, of course, 0. So if I had just a brief xy axis, what I like to do is I like to kind of put these lines out here to show where theta is 0. And what's going to happen is between 0 and 2 pi, and we see this up above too, between 0 and 2 pi, or pi over 2 rather, we complete one full petal. So once you've determined where theta is 0, and you can use, again, these lines to kind of separate everything out, then we go through and we say, okay, well, one petal is going to happen between those zeros, so there's one petal. Here's another petal, and another, and another. Great. Now we have created our flower graph, or our rose petal graph. All right, well, let's go ahead and we'll build on that. It's okay if you're still not quite following. We'll get there. Let's go ahead and sketch a quick graph of y equals 4 sine of 3 theta. That one's going to be a little trickier, so let's analyze this. The 4 out front is going to be the longest, or I guess it's going to be the overall length. I'll need to find a better way to say that. We'll say the length of a petal. Really, it's the longest length of the petal. Okay, so we're going to need to definitely go out to 4. And then 3 theta, because this is odd, we saw this last class, because this is odd, we don't double the number of petals. Well, that's going to be really strange, isn't it? And you might be a little stumped on how to do that. So I'm going to go ahead and actually show you what this graph looks like really quickly. And we're going to bump this one out. Looks something like this. Okay, we have this piece here, and then one that's going kind of straight down on the y-axis. So you might be saying, well, how am I supposed to know that? And that's a great question. It's really tough to especially graph those sine ones, because cosine usually sits on one, if not both of the axes. Sine kind of straddles in between. So let's see if we can come back to this in a quick second and figure out how we could have done that. And to do it, we're going to do f. So we have y equals 4 sine of 3 theta, and we want to determine how many times the graph touches the origin from 0 to 2 pi. We've done that before. Okay, let's solve. And this should say r equals. That's awkward, sorry. So we know we need to set r to 0 to figure out where this touches the origin, and this is usually the process I would use if I'm graphing one of these somewhat accurately. It doesn't have to be perfect. Divide by 4 sine of 3 theta, temporary u substitution, as I think all u substitutions are that we use over these couple years. 0 equals sine of u. And lovely, we just solved this. This one's really easy, right? We saw it was 0 plus pi k. It's the same equation, sign again, nifty. All right, well, if we jump back over here then, we have, instead of u, we had 3 theta, I think this time, equals 0 plus pi k. Divide everything by 3, 0 plus pi over 3 times k. So what values of theta are we interested in? 0, and we just add pi over 3. 2 pi over 3, 3 pi over 3, 4 pi over 3, remember we're going till 2 pi, right? 5 pi over 3, and 6 pi over 3. All right, how does this help us? Well, if I sketch, and actually we have this graph up above, so let's use this guy. These are the points where there's going to be no petal length. So let's take a look. Here's pi over 3. There's going to be nothing on there. Here is 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, and 6 pi over 3. Now looking at this, you might be tempted to say, oh, okay, there are going to be 6 petals here. 1, 2, 3, 4, 5, 6. But we have failed to take something into account that happened on the first graph, and that's where the table comes into play, right? On this first graph, we saw that there was, darken things in like this, we saw that there are certainly 4 petals, but the 4 petals didn't actually necessarily occur in each quadrant where you thought they might. This first one we did in red was all positive, great. But then the next one was negative, and so when we were in the second quadrant, the next one flipped over. And then the third one was positive, so it occurred in that quadrant. By the time we got to this last quadrant down here, we were negative again, and it flipped back. So let's assume we start closest to 0, 0, which is right here. And we know there's a length of 4. So if we kind of split this, it doesn't have to be perfect, but it's pi over 3. So I think probably the furthest length of a petal here would be 4. And that's because of our number out front. So let's turn this into a petal. Great. Now we get to our next quadrant, but it's going to follow the same format every time. In this next quadrant, theta is going to cause sign to be negative. So there's going to be no petal in the second quadrant yet, and it's going to flip down to the bottom quadrant. So we're going to go 4. We have those negative theta values that bring us down here. Cool. So we rotated here, created 1 theta value, rotated here, created another, or I guess a petal down below. So now we are here, third little segment, and we're back to having positive values of theta. So here's 4, and it goes out something like this. There's that one. So now we've rotated here. Now we're into our fourth one. Uh-oh, we're negative again. So if we're negative again, we are not going to create a petal here, and instead we're going to jump back to the first quadrant and retrace that petal. So we're at we're 1/3, we're 2/3 of the way around, and now we're back over here, but we are positive now. And if you're positive, you're just going to retrace this petal. And then we move into the last quadrant of our 0 to 2 pi, but theta is negative again, and so it's going to retrace the petal over here. So knowing that it always is going to go positive, negative, positive, negative, positive, negative can help you create this graph starting from the origin. And so we come up with a final graph of this. But how many petals are there? You'd be tempted to say 3, but if we graph this equation from 0 to 2 pi, there are not 3 petals, and we can see that right here. First petal, second petal, third, fourth, fifth. There are 6 petals here. And it might be a little bit easier to see a visual on this, so I set up a quick Desmos activity to show you, and then we can see what we are going to use this to help us with. So Desmos-wise, we're going to jump you, oh, stop that. We're going to jump you back to 0, and we're going to look at our first equation first. This was 4 sine of 2 theta, and when we created our table, we went from 0 to 2 pi. So look what happens. I'm going by like pi over 6s or something like that up to 2 pi, so we're going right here, and we're starting to create a petal, and you'll notice that we have 1 petal done, and my slider is about 1/4 of the way to 2 pi. Okay, by the time I get to pi over 2, there we go, I've created 2 petals. 3 pi over 2 is 3 petals. 4 pi over 2, 4 petals. Easy enough. All right, but what about the one we just graphed? Here we go. There is 1 petal. Here comes our second petal. And here comes the third petal. And look, we already see the, quote, full graph, end quote, by the time we're just halfway to 2 pi, by the time we're at pi. And now, as I go further, you're not going to see anything else because we're just retracing the 3 petals that we already drew. So it's an interesting thing to look at. If I turn off these sliders quickly, okay, and I'm actually going to retype each of these equations. I think they're going to be useful for us. You'll notice, let's move this up here, that for our first one, when it was r equals 4 sine of 2 theta, that Desmos automatically sets the theta interval to go from 0 to 2 pi, because Desmos knows that it needs 2 pi to complete the full graph. Anything past 2 pi will just retrace the petals. However, if we do the second graph that we looked at, 4 sine of 3 theta, Desmos automatically sets theta to go from 0 to pi because it knows you only need to rotate halfway around to find all 3 petals. Rotating again to go to 2 pi, and we'll put 2 pi here, is overkill. It does the exact same thing because of that positive, negative, r values. Now, if that seems like a lot, that's okay. We're going to make things easier. So here we go. Sample problem. Given the equation r equals 2 cosine of 3 theta, using algebra, determine how many times the graph passes through the origin. Okay, this is you guys. We just did something like this. So go ahead and pause me, and then we will come back together. Ready, set, go. All right, we're back. That gave you a nice chance to practice your u substitution. So we set r to 0. Cosine of 3 theta. Quick little u substitution over here. U is going to equal 3 theta. I'm not changing colors because we're good at this by now. We also divide by 2. And so we find that 0 equals cosine of u. Where's cosine 0 though? I think cosine is 0 at pi over 2. So we find that u is going to be pi over 2. Then the next one is 3 pi over 2. 5 pi over 2, there are these odd multiples, and we need to realize that if pi over 2 is up here, showing on the graph, and 3 pi over 2 is down below, and then 5 pi over 2 is back up here, that we're still moving by pi. Add pi, add pi, add pi, so on and so forth, right? So I think we could probably say that u starts at pi over 2, and then we add pi k. So back over here, we really know that 3 theta is equal to pi over 2 plus pi k. But we need to divide by 3. Should have left myself more room. That's okay. We'll make it work. Multiply by 1/3 instead of dividing by 3 to give you pi over 6 plus pi over 3k. Going one step further, since I know I have to add these together, let's probably multiply by 2 over 2 to get 2 pi over 6k. A little bit easier to add this way. So we start at pi over 6. If you subtract this off, because k can be negative, we get to negatives, and I always like to start with positive theta rotations, especially because we're going from 0 to 2 pi. Pi over 6, add 2 pi k, or 2 pi over 6 to get 3 pi over 6, and just keep adding. 5 pi over 6, 7 pi over 6, add 2 more, 9 pi over 6, that's the same as 3 pi over 2, 11 pi over 6, 13 pi over 6, where is that? Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 pi over 6 is the same as pi over 6. That's too far. That's after 2 pi, because 12 pi over 6 is 2 pi. Great. Using algebra, determine how many times the graph passes through the origin. It will pass through the origin 1, 2, 3, 4, 5, 6 times. Good so far. What's the largest possible value of r generated by this equation? Determine the values of theta where this occurs. Largest value of r. Well, there's a couple ways to do this. Okay, I would suggest that you realize that cosine, the largest answer output you can ever get for cosine is 1. So let's assume that cosine becomes 1 at some point. So if we wanted to maximize r, then really we're just doing 2 times 1, because this is cosine of something, and the largest cosine can ever be is 1, so we get 2. The maximum that r can be is 2. Another way to phrase this is it's the length of a petal. It's just the number out front. We've seen that before. Now, how do we find where that actually occurs? Well, that's different. Let's say that this is r. If we want to find the thetas that create that, just set 2 equal to our equation. Okay, this gives us 1 equals cosine of 3 theta. Oh, hey, look, u substitution time. Let's rock and roll. Let u equal 3 theta. So we have 1 equals cosine of u. And where is cosine 1? Well, that's actually easier. Cosine is 1 at 0, pi, 2 pi, so on. Oh, nope, not pi, though. We just said 1, didn't we? So let's do 0, 2 pi, and so on and so forth. However, can't a radius of 2 also be a radius of negative 2? Right? So couldn't we also set negative 2 equal to this? Because negative 2 just says instead of going 2 this way, go 2 the other direction. So I think we could do positive or negative 2 here. And so if we're looking for plus minus 1, right, maybe it's better to see it this way, then what we can do is start building those back in. So 0, pi, 2 pi, and so on and so forth, yeah? Great. And so if we drop this back over to 3 theta again, we say that 3 theta is equal to, this is u equals 0 plus pi k, so 0 plus pi k, divide by 3, 0 plus pi over 3k. All right, so if we wanted to take a peek at our theta values here, 0, pi over 3, 2 pi over 3, 3 pi over 3, and so on, so forth. Whew, that took a lot of effort. Let's go ahead and get this graphed. So pi over 6's look like this. Here's pi over 6, 3 pi over 6, 5 pi over 6, 7 pi over 6, 9, and 11. There we go. Those are the potential areas where our flower petals can be drawn. However, we also know that these guys are going to be the lengths of our flower petals. Now, it's probably not a bad idea to at least try 0 in the original equation to see if we're positive or negative so we can start to see that alternation. So if we plug 0 in here, 2 times the cosine of 3 times 0, we get 2 times the cosine of 0, or 2 times 1, which is 2. Positive. Love that. So at a rotation of 0, there's a length of 2. That's the largest petal, or the largest length of a petal, so we can see that our petal looks like this. Next quadrant, theta is going to be negative. So we started here, went over here, theta is negative. So now we're going to draw this. Okay. Oh, 9 pi over 6. Oh no, that looks good. Okay, so our next one we are going to draw down here. Okay, and it looks something like that. Looks pretty good so far. And then our third quadrant, we're positive. And so our third quadrant, 2 pi over 3, is going to be this guy right here. We have our next petal. Fourth quadrant is negative. We're in here. So negative is going to redraw the original petal. We don't need to do anything. Fourth quadrant positive, fifth quadrant negative, sixth quadrant positive, so on and so forth. I think that is probably our final graph. Okay, let's see how we did, and then we can probably answer the next question pretty quickly as well. Moving through. There we go. Alrighty. So we had 2 cosine of 3 theta. Fingers crossed. Look at that. I think we did pretty darn well. Yeah, that looks really, really nice. Well done. Alright, how could you alter the equation so that there are 5 visible petals? Well, 3 right here made 3 visible petals. I think we could just change the 3 to a 5, couldn't we? Hey, look. 5 visible petals. We're rock stars. What about 8 visible petals? Well, you might initially be tempted to say, let's just change it to an 8. Oh, but we need to remember that the value that's here, we always double it. But if it's even and you double it, you will see all of those petals. So this is 16 petals. If it's odd and you double it, there are 6 petals here from 0 to 2 pi, but you're only ever going to see 3 of them. So if we want to see 8, we need 4, and that'll show us all 8 of those. Okay. Now, you might be looking at this going, oh my gosh, there is so much to learn here. Do we need to do all of this all the time? Certainly not. So realistically, I think E and F are pretty popular, and then maybe something like, oh, and we didn't even do an example here. We'll do it on the next page. So let's take a look at E and F. We'll do one example, and we are done with this. So find the value of dr d theta when theta equals pi over 4 and interpret the result in context of the graph of r. Okay, well, r equals 2 cosine of 3 theta. And if I'm going to find dr d theta, it's like we're doing dd theta of each side. Derivative of cosine is negative sine, so I'm going to throw the negative out there. And then don't forget the chain rule. So this really gives us negative 6 sine of 3 theta. They want the value of dr d theta at pi over 4. So that becomes negative 6 times the sine of 3 times pi over 4. Well, that's 3 pi over 4, and sine is positive in the second quadrant, so negative 6 times root 2 over 2, or negative 3 root 2. What did we just find? Well, if we look at our graph at pi over 4, so pi over 4 is right here, so we rotate it here, and they're saying, what's happening to our graph? Well, our graph is all the way down here. Here's the piece at pi over 4. I should use a different color. Sorry. Here's the point at pi over 4 because it's popped over to the negative realm. And they're saying that dr d theta is negative 3 root 2. So what ended up happening here is because r is becoming more negative and we're up here, more negative actually means that the radius is increasing on a negative side. So we have this radius length right here. The next radius is going to be even more negative, or in the context of this problem, larger. And then larger, and then what's going to happen here is now we're going to be getting less negative, so the radius is going to start to shrink. Last but not least, write the equation of the line tangent to the graph of r at theta equals pi over 4. Ooh, this is a dy dx problem. Here we go. dy dx is found by doing dd theta of y over dd theta of x. And we need to remember that y is the same as r sine of theta. Easy for me to write. And x is dd theta of r times the cosine of theta. Again, I never have this memorized. I always have to write it out. So we do the derivative. Derivative of r, right? Product rule time. So the derivative of r is dr d theta, and we keep sine of theta the same. Plus, now we keep r the same. The derivative of sine is cosine. Divided by dr d theta. Keep cosine the same. Hold off on the plus because this always happens. We keep r the same. The derivative of cosine is negative sine, and I'm just going to throw the negative right there. Perfect. Now we need to evaluate this at pi over 4, but it might be worthwhile realizing that we've already evaluated dr d theta at pi over 4, right? We did that down here. Since we're going to also have to evaluate r at pi over 4, let's just tackle that right now. R of pi over 4 will be 2 times the cosine of 3 pi over 4, which is, and I'll have to work down below, 2 times, let's see, the cosine of 3 pi over 4 is negative. Cosine is negative in the second quadrant, root 2 over 2, which is negative square root of 2. All right, so keeping in mind we already know these two values, I'm just going to highlight them down here. We can now find dy dx at pi over 4. Okay, so dr d theta we found, and I did that in green, it's going to be there twice. So that'll be negative 3 root 2 and negative 3 root 2. Should probably throw our fraction line up there. There we go. Sine of pi over 4 will be root 2 over 2. And cosine will also be root 2 over 2, minus plus. R of pi over 4, well, that's what I did in red down here. That's going to be negative square root of 2 on each of these. And then cosine of pi over 4 is root 2 over 2 and root 2 over 2. Looking good. Can we clean this up? Sure. Do we have to? No, but might as well. This becomes 2, and then 2 divided by 2 is 1, so those are gone. Same thing, that's gone as well. This is going to become a plus. This is going to become a minus. This is 2 over 2, which is just going to become 1. So we have minus 1, and this is also going to become 1 over here. So I'm looking at, look at all those square roots that are canceling out. How exciting. Negative 3 minus 1 over negative 3 plus 1. So I have negative 4 over negative 2, which is 2. Excellent. That was actually a really nice derivative. But then we still actually need the tangent line. So our tangent line is going to be found by doing dy dx evaluated at pi over 4 times x minus the x value at pi over 4 plus y of pi over 4. Whew. Okay, let's fill some of this in. We already just found that dy dx was just a nice positive slope of 2. That was cool. But I think these two, x of pi over 4, maybe we remember that x is r times the cosine of theta. Yeah? So if we want to find x of pi over 4, we already evaluated r at pi over 4. That was negative square root of 2. And then cosine of pi over 4 is root 2 over 2. These make a 2. 2 over 2 is negative 1. So we have x and then 2 negatives plus 1. And then we do our y value. So y equals r times the sine of theta. It'll be a very, very similar process. So y of pi over 4 becomes, we already found r, negative root 2, and then this is also root 2 over 2, so it is again negative 1. Wow, tangent line. Is that right? Fingers crossed that we did everything well. It is 2 times x plus 1 minus 1. I'm going to wait for my computer to sync up. There we go. Y equals 2 times x plus 1 minus 1. You're like, oh, that went through the graph, but this isn't our graph. Didn't we make it 3? And look at that. We have an awesome tangent line bouncing off this point right here. And you're like, what? That's not pi over 4. Well, don't forget, though, that our equation was this guy over here. And we found when we substituted in pi over 4 to r, we got negative root 2, right? So if we wanted to check that x value, it is r, so negative root 2 times, and then we have the, so our x value coordinate is right here, right? Oh, it's negative 1, negative 1. I guess we already did all the math, so let's just do that. Negative 1 comma negative 1. There we go. There's our point. There's our tangent line. We have done brilliantly. Now again, you're probably saying, how much of this do we need to do? Not that much. And in fact, on your practice for today, it's even faster. The practice asks you to identify an equation and find the interval of theta, which creates only one petal, which is way less work than we've done so far. Equation first. Looking at this guy, I can see it's around the y-axis here and nothing else, so I know it's already going to be something with sine. I only see 3 petals. That's an odd number, 3 theta. I also see the length of a petal, because we have the x-axis or the y-axis here, is 3. There's my equation. Easy, easy. You can check that on Desmos. How do we find the interval that creates only one petal? Well, we use the fact that petals occur in between when we get to 0, 0, 0, 0, so on and so forth. So we just do a quick, let's set our equation equal to 0. So 0 equals sine of 3 theta. Quick u substitution. We've done this before. So u is going to be 0, pi, 2 pi, and so on and so forth. And so we're going to go through here and say that's 0 plus pi k. And then we unsubstitute, resubstitute, something like this. Divide by 3. It's really easy when it's 0, too, because now if we look at our values of theta, 0, pi over 3, we're just adding pi over 3 every time, right? And so on and so forth. We could go forever, but we just need one petal. And to create one petal, it's just any 2 consecutive theta values, 0 to pi over 3. Great, there's our answer. That's the interval of theta, which would create one petal. You could have said pi over 3 to 2 pi over 3. That works too. And just to show that again visually, let's take a quick peek at the graph of 3 times the sine of 3 theta. And then I'm done talking at you. You have a couple practice problems left, and that is it for today. So we're looking up here. We're changing this a little. We said it was 3 and then sine of 3 theta. Looks pretty good. Matches our graph. Excellent. And we said one petal is created by going from 0 to pi over 3. So let's go 0 to pi over 3. Haha, one petal. I did mention you could have gone from pi over 3 to 2 pi over 3. There's another petal, and so on and so forth. So realistically, if you can do this process on A and get through E and F, then you are golden. Thanks for hanging in on our deep dive on rose petal graphs. Sorry that it took so long for today, but you're going to come out of this better than ever, especially once we start getting into our area of polar graphs.